So we said because the signals are low level and they vary very slowly with respect to time, said that they can be considered to be DC signals or very slowly varying DC signals can work up to the DC frequency range. We use an amplifier that can work up to the DC frequency range. Most of the amplifiers you studied in their third year we saw that only an emitter coupled amplifier is capable of amplifying all the way to DC. The other name of emitter coupled amplifier, we call it a differential amplifier. And in the last class, I showed you that the best example of a good DC amplifier is to use an operational amplifier. So you select an operational amplifier. These were called operational amplifiers because they were used to perform mathematical operations. Actually, they're the ones we are used in our analog computers. However, the operational amplifier, even a modified one, which is called an instrumentation amplifier, the difference between a general operational amplifier and an instrumentation amplifier is that the instrumentation amplifier is actually optimized to be very, very low noise. So they make sure the transistors which are inside, as much as possible, especially those in the differential pair, and they generate very little noise. In the last class, I talked about the various types of noises generated inside this type of amplifiers. The resistors themselves generate noise. The resistors that are used actually to bias and couple the transistors inside the amplifier, they generate noise. And the different type of resistors generate different types of noises. The highest quality resistances are those made from metal oxide. They're called metal oxide resistors. The cheap ones that we normally find sold in shops, or the types used in your labs, those are carbon resistors. Those generate a lot of noise. But even if you've selected the best instrumentation amplifier, so that you can minimize the noise, and this noise, the frequency band of this noise are normally much, much higher than the input signal that we want to amplify. So even if you select the best instrumentation amplifier, we still find it suffers from VIO drift and IIO drift. And when these are referred to the input of the amplifier, they're of order of magnitude with the signal that we want to amplify. So this VIO and IIO presents to us the biggest problem. VIO drift and IIO drift is normally a function of temperature. So for example, in Nairobi, if in the labs, for example, maybe early in the morning, the temperature could be maybe 15 degrees centigrade. In the afternoon, it could be maybe 22 to 25 degrees centigrade. And that will affect what is coming at the output of your transistors or your overall amplifier. instrumentation amplifier. So in this paragraph over here, I would say that practical DC amplifiers, e.g. op-amps, I can even add instrumentation amplifiers, are not suitable since they suffer from drift. I could add maybe drift voltages and currents, i.e. variation of VIO with respect to time and variation of IIO with respect to time, which are order of the signal to be amplified. Which are order of the signal to be amplified when referred to the input. The manufacturer of the op-amp can give you this VIO and IIO with respect to the output of the amplifier. If you know the gain of the system, you divide that value and get what is that VIO with respect to the input. And then you compare it with the signal that you want to amplify. So we find that typically their magnitude is almost equal to that of the signal being amplified. So that if you got a monitoring circuit at the output of your system or of your amplifier, and the output will be equal to some gain times the signal that you want to amplify plus VIO, or the effect of IIO at the output. So I've said the implication of this is that the processing circuit at the output of the amplifier cannot differentiate between the input signal and the signal from the offset voltage or current. So you've got to have a way of how to discriminate between the useful signal and the noise signal. So in this case, the noise is predominantly due to VIO or due to IIO. And then when you find in the last class what VIO is due to the imbalance of VBEs, and IIO is due to the difference in the betas of the two transistors. And then we said that one way would be to put your amplifier in a controlled bath, but this technique is expensive, even though it achieves drift voltages at the output of order 1 microvolt per degree centigrade when referred to the input. And a cheaper and higher performance alternative is to use a chopper stabilized amplifier, which provides superior temperature and drift performance. So we come to our topic. What is the superior technique? So the superior technique is to use a chopper stabilized amplifier. In short form, I'm going to be calling it the CSA. Chopper, C for chopper, S for stabilize, A for amplifier. So the chopper stabilized amplifier comprises of 3 modules. Maybe I'll just draw it over here, although I've drawn it towards the end. It comprises of 3 modules. And just so that you can visualize it, I've drawn it towards the end. I'll just draw it over here. So input is V of t, such that the V in of t dot t is approximately equal to 0. So the first stage is the modulator. The second stage is what we call the AC amplifier. And that stage is a demodulator. The AC amplifier is just similar to your typical high quality op-amp with the capacitors for DC blocking. And the modulators, normally we use a pulse amplitude modulator and a pulse amplitude demodulator. So you got to revise a bit of your telecoms that you studied, the various modulation techniques that I'm sure you studied in your telecoms, such as A modulation, DSB modulation, maybe FSK, DPFSK, QPSS, QP, quadrature, phase modulation, and other techniques in your telecoms. But here we'll just concentrate on pulse amplitude modulation. So the chopper stabilized amplifier comprised of the following: a modulator, which is the first stage. So the signal flow is in this direction. So the first stage is a modulator, which will convert our slow varying signal into a pulse amplitude modulated signal. The second stage is our AC amplifier. It's called an AC amplifier because only AC is allowed to be amplified by our direct couple amplifier. The amplifier itself is actually like an instrumentation amplifier. So it's a DC coupled amplifier, but you want only AC to enter it. So we use these capacitors, which are drawn over here, both at the input and the output. Okay, so the capacitors will prevent any DC, maybe due to offsets of your modulator, passing into the stage, into the input of this AC amplifier. And this capacitor, the output of our system, will also prevent any offset variations inside our low noise amplifier over here, passing through the output. And then we demodulate the signal and get our amplified signal over here. So let's go as shown in the notes over here. So this is the function of the modulator. Now, normally I ask this in exam and very, very few students get it right. Very, very few students get it right. Now, the modulator converts the slowly varying DC signal into a higher frequency that is amplitude modulated, which is then amplified by the AC amplifier. Now, the way we effect this conversion, is by chopping the signal. So a simple amplitude modulator is effected by chopping the signal with a switch controlled by a square wave, or it can be a rectangular wave at the desired frequency. Typically, this should be greater than Nyquist rate. Now from your telecommunication, you know what Nyquist rate is. Nyquist and Shannon came out with the information theory that in order to reconstruct a signal which has been sampled you got to sample it at least at twice the lowest frequency component. Sorry, at twice the highest frequency component of the signal. So for example, if the input signal, or say 1 kilohertz, and you sample this signal, for me to reconstruct this signal with little distortion, I need to sample it at least 2 kilohertz. But that is at the limit, not practical. In most cases, we want the reconstructed signal to have minimum distortion. So we sample it, or we sample it at a higher frequency than that of Nyquist rate. So I've written over here, however, for the reconstruction of the signal with minimum distortion, this should be at least 10 times that of Nyquist rate. In your telecommunication, I'm sure you came across Nyquist and Shannon. Sometimes this is known as Shannon's theory. Sometimes it's called Nyquist rate. For example, now I'm speaking to you through a microphone in the laptop. For you to hear high quality sound, you find it sampled maybe at 44 kilohertz. For a normal male voice, maybe the maximum frequency is only 6 kilohertz inside it. So if you're sampling it at 44 kilohertz, means 44 divided by 6 is how much? Is it 44? 6 times 8 is 48, approximately 8 times. Normally, the higher the sampling frequency, the lower the reconstruction distortion, the higher the quality of the recovered signal. So there's somebody whose microphone is on and is disturbing us. So in this last paragraph, I chopped or sampled output signal appears at the output of the switch, hence the name a chopper. So down here, I've drawn a simple diagram of a chopper, or the modulator of the chopper. Down here. So this is your switch. Sometimes you call it the chopper switch. So when the switch, so this is your input side. This is your input side, and this is your output side. So this this rectangular waveform over here, we normally call it Vc of t. C there stands for control voltage. So in the olden days, this switch could be a relay. In the early 60s, this could be actually being activated with a relay. So your Vc of t would control the switch. So when it's high, the switch is closed. When it's low, the switch is open. And so in the early 60s, that's what they would do. So this S over here is called the chopper switch. So when it closes, but the signal passes. When it's opened, the signal is interrupted. So we say that the output is a chopped signal of the input analog waveform. So let's consider the requirements of a chopper switch. Okay, like maybe if we just to draw some hypothetical, let's assume this is our input signal, very slowly varying input signal. So this is the amplitude of our signal. And this is the time axis. And let's assume this is our VC of t. So if our switch is, this is the frequency, for example. So during this interval over here, this, if the switch is high, when VC of t is high, the switch is closed. And this is your V naught, the output of the switch. So you're going to get something like that. So there'll be some almost rectangular waveforms at the output, which are chopped versions of the top input signal. And that is actually a pulse amplitude modulated signal. Actually, a pulse amplitude modulated signal. Now, this would be a revisions of telecoms. How do we get the spectrum of the chopped signal or the pulse amplitude modulated signal? V naught of F or V naught of omega if you want. How do we get supposing my input signal, the input frequency spectrum is Vi of F. The control signal is Vc of F. So in the time domain, V naught of t is equal to Vi of t times Vc of t. So how do we get V naught of F? How do you get V naught of F, somebody? When you multiply two signals in the time domain, how do you get the spectrum of the signal in the frequency domain? You must have done it in your telecoms. Anybody?
Could it be convolution?
Yes, you got to have convolution theorem. You got to apply convolution theorem. So all of you go and revise convolution theorem from your telecoms. Okay. You have to use convolution theorem. Another way to look at the problem is to resolve each of the signals in the time domain, so that you get all the sinusoids of the two signals. So for example, if the first signal, our low frequency signal, let's assume, just for matters of simplicity, let's assume it was a 1 kilohertz signals, right? And then let's assume our control signal was 10 kilohertz signal. So if you don't want to use convolution theorem, if the first signal is a pure sine wave, then you got to resolve the control signal into its harmonics. Now, if Vc of t is a square wave, as shown over there, you get to get the spectrum of a square wave. So for the square wave, you know you can split it using Fourier transform theorem into its comprises of fundamental and all the other odd harmonics. So if Vc of t was a 10 kilohertz square wave, then you get the fundamental at 10 kilohertz. You'll get another harmonic at 30 kilohertz, 50 kilohertz, 70 kilohertz, and you got to use the sync function to get the amplitudes of the harmonics of this square wave, to get the amplitudes of the harmonics of the square wave. Then you multiply in time the first frequency of the input, which is 1 kilohertz, times 10. So you'll add, subtract, because now it would be a DSB signal. So you'll get a spectrum, 11 kilohertz and 9 kilohertz. You repeat the same with the other harmonics of 30 kilohertz. Then 50 kilohertz, 70 kilohertz, 90 kilohertz, etc. Of course, it will be diminishing according to the sync function. I hope you all know that the sync function looks something like this. So that's how amplitude varies with frequency for the rectangular waveforms. As the width of the rectangular waveform becomes very thin, then the sync function expands, and at the limit it becomes just flat. You get all the spectra. So that is how frequency translation is effected. I'll demonstrate that with a simple example after this. So in this diagram, V naught T, the pulses of V naught T, will have a fundamental frequency that of Vc of t, and then all the other odd harmonics if Vc of t is a square wave. So please go revise the sinc function that you did in your telecoms. So if you look at these diagrams I've drawn towards the right, the input is a slow varying waveform. The control signal are rectangular pulses of a high frequency. The output of our switch is a pulse amplitude modulated signal. So the spectrum of our pulse amplitude modulated signal is totally different to that of our input signal. Okay, so that's the function of this chopper switch. This chopper switch chops the input signal to get a pulse amplitude modulated signal at the output. Now let's go deep into the requirements of this switch over here, of this switch, the chopper switch. Now the ideal chopper switch should have the following characteristics. Number one, it should have a zero on resistance, because you don't want part of our input voltage being lost across the switch. It should also have an infinite off resistance. So when the switch is open, no signal either from the control signal or from the input should pass to the output. Number three, it should be capable of high-speed switching when that is a requirement. Number four, it should have good isolation between the control voltage Vc of t and the output terminals of the switch. Of course, here I've drawn it very simplistically. In the olden days, as I said, we'd use relays. So this control voltage will drive a relay, and that relay will attract the switch to close or open. So we don't want any control voltage appearing at the output of our switch, otherwise give rise to errors. Then the switch also should not have an offset voltage at its output. We shall see how this comes in later on. Of course, with things like relays, there's no offset voltage. When a relay is open, it's open. Unless you ionize the contacts, if it's the contacts of the relay is air. For those of you who are doing power, you should know that maybe to ionize 1 centimeter of air requires how many volts? About 15 kV, kilovolts. But for us, our input voltage is 50 millivolts, so air is not a problem. Ionization of air is not a problem. Next, the output terminals of the switch should not suffer from drift. And then ideally, the switch should have zero control power. It means the power required to activate the switch should be zero. Because we shall see later on that this is actually not the case. But here I'm talking about an ideal switch. Then we compare them with the practical switches. And lastly, the switch should be able to pass infinite current when on and block an infinite voltage when off. So those are the ideal requirements of the switch. But in practice, we deal with the real components. And we'll start with the earlier switches that we had in the 60s. So these are the practical switches, which are non-ideal. And the first set of switches are called the electromechanical relays, which was actually what was used in the early 60s. And the relays are of two types. You have the normal relay, then we have the reed relays. I think some of the normal relays you've seen in the machines lab and also in the measurement lab. The reed relays that are actually quite tiny. They look like a diode. They look maybe something like this. I don't know if my pen is selective. They're actually very small. They're the size of, let me just magnify it so it looks better. They're the size, I don't know if you've seen some detector diodes. So this is normally in a glass bulb, which is vacated. Then there's a winding around it. So these contacts inside the glass are magnetic. So when you put a magnetic field, the two will attract each other and close. But the size is very small. They are normally around, if you've seen this 1/8 watt resistors, they're that size, quite small. But since the moving parts inertia, the weight is very small, you can open and close this switch very fast. So those contacts inside are flexible. They are made of spring material. So when there's no activation, there's no current passing through, they're apart. The power required to activate them is very small, unlike the normal relays that we have. I'm sure you've seen some in the measurements lab. So what I've drawn over there is referred to as reed relays. And they're quite rare. So the only difference is size. And therefore, the power required to activate them, and therefore the speed at which they operate, because the moving parts are very light. So let's start. Our electromechanical relays are two types. You have the normal relays, and then you have the reed relays. What I've drawn over here are the reed relays. Now, the advantage of electromechanical relays as follows. The on and off switching characteristics are close to that of the ideal switch. I should have typed over here ideal switch, because when they're closed, the resistance almost zero. When they're open, the resistance almost infinity. That's if you don't ionize the gas inside. Next, they do not suffer from drift at the output of the terminals, because they're just contacts. When it's closed, the resistance zero. When it's open, the resistance almost infinity if you don't ionize the gas inside it. Also, they've got good isolation between the control voltage and the output terminals. So like in this one, which I've drawn over here, VC of T will be connected between these 2 points. This is here VC of T. And none of that voltage can appear at the output of the switch. Now, the disadvantages of these electromechanical switches are as follows. Due to the fact that the switch have moving parts and therefore have mass, they have low switching speeds, typically below excuse me, typically below 60 hertz for the relays, and below 400 hertz for the reed relays. Also, the slight distortion in the reconstructed signal at the demonitor, because unless the switches are finely tuned, I think there's something missing there. They give rise to distortion at the output due to contact bounce, because when the switch closes, due to the mass of the, especially the heavy switches, the normal relays, because of the inertia of the contacts and the weights associated with the part of the contact, they tend to be contact bounce. Oh, the normal relays, if you've seen them, if I can just draw maybe a side view of those ones, they tend to look something like this. And then they've got an armature. if I've drawn it well. You have a winding. So the mass of all this will have to move. Will have to move. So because of the inertia, if this is the fixed contact, this is the fixed contact, then when this part is attracted, top part is attracted, tends to not just close only, but it tends to bounce before settling down. So that can give rise to the reconstructed signal. And even at the demodulator, it can also give rise to a problem. Next, because of their size, it results in a bulky chopper construction. Because of the mass of this relay, it's heavy. It will require a lot of energy, in fact, to activate it. And therefore, the last point over there, it requires high power to drive them, leading to high power consumption. And it's not suitable for things like meteorological stations, which are located in remote areas, whose only source of power could be maybe solar. So in the early 60s, they'd use this. Maybe up to 1965, they'd use these reed relays. But nowadays, we don't use them because of their disadvantages. Now, the other type of switches are the semiconductor switches. So instead of using electromechanical switch to perform your pulse amplitude modulation and demodulation, you can use semiconductor switches. Now, the semiconductor devices which you can use as switches, we have the BJT transistor, we have the field effect transistor, we have the metal oxide field effect transistors. If we start with the first one, which is the BJT transistor, BJTs, I'll just read what I've written over here. I've said that although BJTs have a high switching speed, they, however, have large offset voltages at the output terminals of the switch of order 0.1 volts for germanium and 0.2 volts for silicon transistors. I'm sure you people studied logic gates in your third years. And if you're using silicon transistor, when it's on, you find there's an offset voltage of about 0.2 volts for small signal transistors. But germanium transistors are very rare nowadays. So for transistors like BC107 and BC108, if you're passing about, if it's on, they're passing maybe 10 milliamps even, the voltage across it will be about 0.2 volts. Now imagine, supposing this is our circuit, and you put your BJT switch in series. Let's assume it's a series switch. We shall come later in details about the topology. Now the input we want is 50 millivolts, slowly varying DC. This is your switch. Now if it's going to lose 0.2 volts across it, which is 200 millivolts, then you've lost all the signal. Nothing is going to come out over here. The voltage at the output of your switch will be 0. So when the transistor is on, it will drop 200 millivolts across it. So if you're putting 50 volts on the other side of the switch, nothing is going to come out. And then the other problem with the BJT switch is that it only switches in one way. Switch. So when the input voltage changes to minus 50 millivolts on the other side, that switch won't be able to work. So I've said that although BJTs have a high switching speed, they, however, have large offset voltages at the output terminals of order 0.1 volts for germanium, 0.2 volts for silicon. This offset voltage is much greater than the signal to be passed through, i.e. 50 millivolts. Also, BJT transistors are not bidirectional, i.e., they can only chop in one way. It means if it's an NPN, then the collector must be positive. If the collector goes negative, the circuit fails to operate. So because of this, we never use BJT transistors. We never use BJT transistors. Now, I don't know if you got a class after this. You see, as the years come, I'm seeing only 38 people coming. Any CR there? You can switch on the mic.
Yes.
So fine. I've got a
Yes.
problem with the list that you gave me. You gave me the same list that you sent me before of the emails.
Oh, it was the same one.
Yes, the same one.
I'll look at it. I'll add the ones for those who hadn't given their
No,
email.
don't add. I want you to separate it, so that it's only those ones I'll add.
Okay.
Only the students which did not get an invite.
Okay.
Okay.
Yes.
I don't want the whole list again. You have a class after this, or I can finish. I'm talking to the CR stuff. Huh?
We have a class.
Okay. And why are you so few? I'm only seeing 38 of you. What are the rest of you?
I'm not sure. Maybe they thought they wouldn't be a class due to possibly the strike.
Did you have some classes in the morning?
Those doing power had a class, but for labs, they weren't able to have labs.
Okay. Okay, then we'll end over there. We'll end over there for today.